Hello, in this video, we are looking at how we can find the length of a curve defined by a function. So suppose we have some function defined from A to B, and we want to find how long this curve is. Well, using the strategies of integrals, we can slice up our interval into small little sections of these x sub 1, x sub 2, and look at just any generic section from slicing up that interval. Then, approximating the length of the curve on that interval would be the same as finding the length of this segment. Well, we know ways to find the length of that segment can either use the idea of the distance formula or the idea of a right triangle. We're going to look at it in those right triangle sense, where the distance between the x coordinates is our little distance delta x, and the distance between the y coordinates is the distance between the function values, or we can call that delta y sub I. That's going to vary depending on the interval, but it's going to be some small little change in y. So this line segment, we're going to call Li, and set up with the Pythagorean theorem, that length that we're trying to estimate is the change in x squared plus the change in y squared. And since we have a positive distance, we are looking at the square root of this delta x squared plus delta yi squared. Now, typically, when we're wanting to use this integral, we want the delta x outside so that when we take the limit of the sum of all these little pieces, that delta x turns into a dx. So I want to try and factor that out so I can get it all the way outside the square root to use the integral. So I'm going to first factor out the delta x from everything. So factoring out a delta x squared from delta x squared leaves with 1. And then factoring out a delta x squared from delta yi squared becomes delta yi over delta x squared. So undoing some distribution. And now, since everything has this squared term multiplied by it, we have L sub I is equal to that square root of 1 plus delta yi over delta x squared delta x. Now, when we take the limit of the sum of all these little li's, this delta x will turn into our differential. But we still have this delta yi over delta x piece. But we're not sure what that is. But all through Calc 1, we talked about this idea of the slope of the tangent line. And what a little change in y is over a little change in x is ultimately the derivative at some point xi star that's between these xi and xi minus 1. So somewhere in here, there's this xi star where the derivative at that point is the same as the delta yi over delta x. And since these intervals are really small, ultimately, that means that we can replace out these delta yi over delta x with the derivative at xi star. So replacing that out, we have that these line segments L sub I is the square root of 1 plus the derivative at some value x sub I star squared delta x. Now, taking all those L sub i's and adding them up from I equals 1 to n. And then taking the limit of those as n goes to infinity, so making the interval really, really small, this will be the length of the curve overall. This is our formal definition of what the integral is, so the length of the curve along the y-axis is the integral from a to b of the square root 1 plus f prime of x squared dx. And now we have a formula we can use to find the arc length of a curve, and we will see how to use that in some examples in the next videos.